Hello everyone. Hope you all had a good day so far. Here we are at week 5. Week 5. So we're going to be talking about loops for a couple of weeks. It's this week we're going to be talking about the while loop and the for loop. And then next week we're going to be applying them in some common algorithms. Right? I do want to mention that this is probably the part of the class where it's easy to fall behind. This is because we're finally going to be writing programs that can repeat certain pieces of code. In the previous projects, we've only wrote like very flat programs, like they start from the top and then they end at the bottom. But today we're finally going to be able to see possibly infinite control flow. So this is the harder part of the class, especially when the algorithms come next week. There's something called algorithmic thinking, and let me pull up a definition. Computational thinking. One of the trickier parts of a computer science class is algorithmic thinking. You can think of this as a way of organizing your thoughts into representing them as computational steps that the computer can run. All right. So next week we'll have a lot of exercise on this computational thinking. Okay. I have a couple things out. The supplementary material. These are the suggested readings. I highly suggest going through them. I haven't found any. I haven't filled this one in yet. The common algorithms. I'll find something soon. All right. But if you look at the back of if you go through the readings, they're gonna have some exercises here and there. So the common algorithms will pretty much be already in these sections. But we'll go over more algorithms later, like statistics and looping input. All right. Okay. So yeah, let's talk about loops. First, I wanted to define this word that I'll use a lot. This iteration. You can think of an iteration like a generation, like it's a part of a cycle. All right. In computer science, we can think of an iteration as a single cycle that we're probably going to be repeating. So, and this iteration will help us approximate some sort of result. All right. So yeah, I did say that you can think of iteration like a generation. The reason why is so I can motivate some sort of AI training. AI is a very popular topic nowadays. So I'm going to motivate it with this quick video. This video is about reinforcement learning. AI is a umbrella term, as it encompasses a lot of different things. One of it is reinforcement learning. You can think of reinforcement learning as iterating through multiple generations, and each future generation should get better and better. It's kind of like how humans learn. We learn through kind of like reinforcement. We gain a reward, so we learn from it, or we get a punishment and we learn from that. So that's kind of like a reinforcement learning. Let me just play this video here so people see what I'm saying. Okay, so this video right here is showing two bots playing against each other. So there's this hide and seek game. We have two teams. We got the hiders and the seekers. So the point of this video is to show how you can train agents to find the optimal solution. And how they do this is by iterating through many generations. The generations learn from rewards and punishment, and they get better and better. All right, so I'm going to play this video real quick. This is the author is OpenAI. I believe this video came out before ChatGPT became popular.
On Earth, the simple rules of natural selection and competition led to the evolution of increasingly intelligent life forms. Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter. In the last stage of emergent strategy that we observe, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide and seek in parallel for many days. They train against each other as well as past versions of themselves using an algorithm called self-play. Coevolution and competition on Earth led to the only generally intelligent species known to date, humans. While this world is far less complex than Earth, we have found evidence that simple rules can lead to increasingly intelligent behavior from multi-agent interaction. We hope that with a much larger and more diverse environment, truly complex and intelligent agents will one day emerge.
Cool stuff, right? So yeah, once again, this was an example of training an agent to get better and better. These are not actual humans playing. I know it does look like people are controlling it, but these are automated. All right, pretty cool stuff. If going on a slight tangent, folks might have heard about the Super Mario record being broken by an AI. This is trained through reinforcement learning. There is an agent, a Super Mario agent, that was trained through millions of iteration, and they were able to, they're way better than any human can play. So let me just look up something real quick. Reinforcement learning Super Mario. This is pretty cool stuff. You can train Super Mario to beat the world record. So if you want to take a look at this video on your own time, you can. Pretty much they go over training Mario to get better. So right now this is not human playing it. It's a computer playing it. If you look at the top, there's some information here. It says, okay, this is generation 34. This is species number 14, and this is genome 14. So these numbers are really just kind of keeping track of each bot's iteration, because this is going to be played a million times, but probably even more. So the top here is kind of labeling where they're at in the training. All right, so yeah, you can watch this up on your own time. It's pretty cool. And yeah, Super Mario ends up beating the world record. Okay, so yeah, I just wanted to motivate it a bit. You can think of that as that training as like a loop. The loop is pretty much running it over and over again, and it's up to the designer to stop the training whenever they want. Okay, so with that in mind, let's go ahead and introduce the while loop. Okay, so we saw a while loop last week, by the way. We got a very small sneak peek into it. This right here, guessing game. So if you want to take a look at last week's material, we wrote a guessing game the point of this was to introduce a while loop. But today we're gonna go a little deeper into it. Okay, so here let me give a general outline first. First we'll introduce the while loop, and then we're gonna do a couple examples. One example is going to be simulating compound interest. This means we're going to be simulating a bank account that gets bigger and bigger. All right, and then later on, towards the end of class, we'll do a roulette simulator. This is really just going to be a glorified guessing game. Last week we did this over here. So let me just pull up this guessing game here. So this was stuff from last week. Let me go ahead and compile it and run it. So cd into examples and compile and run. Cool. So here's a guessing game. 5 is incorrect. 6, 7, 8, 9 is incorrect. 0. Okay, 0 turned out to be correct. So we're pretty much going to be rewriting that guessing game, but it's gonna look a little cooler. We're gonna add a new variable, like a bankroll variable. All right. So yeah, that's pretty much the outline for today. Okay, let's go ahead and introduce this while loop and then apply it. So a while loop is just like an if statement, except there's a loop in it. It's just like an if statement because if the condition is true, we're going to enter the local scope and perform the statements. The loop happens when all of the statements are done. We're going to check the condition again, and if it's true, we'll do the statements again. So we're going to loop this over and over again, and maybe at some point the condition will be false. And when that condition becomes false, we will finally terminate the loop and exit the scope. All right. So let's go ahead and apply this real quick. We're going to simulate years. Right now it is 2026. So let's go ahead and write a loop that goes through multiple years. Okay, this is going to evolve into a compound interest example. So I'm gonna go ahead and make a file for this. All right, I'm gonna make a file. I'm gonna call it compound interest. Let me put it in this folder over here. Okay, I'm gonna call it compound interest.java. Okay. First step, we're just going to write a loop that lets us visualize a year getting bigger and bigger. All right, so let me go ahead and set it up. Let me set up this main over here. Okay, for now, I'm gonna hard code a year. So the current year right now is 2026. This is hard coded. It's probably a better practice to pull this number from the actual clock. I forget the exact syntax for it, but a better programming practice would be to pull from a clock. There's probably like a library. I forget what it's called. It's probably called like date time, and then it's got like a method called like get year or something. I forget what it is, but I'm just gonna hard code it temporarily at 2026. Okay, and we're gonna simulate the years getting bigger and bigger. All right, so for now, I'm gonna do a while loop with a, and I'm also gonna hard code a true condition in the top. The reason why I'm hard coding a true here is so we can start off with an infinite while loop. All right, so this is a condition that's always true. We're forcing an infinite while loop. And here I'm just gonna do a print statement. Just print out the year. The year is, and then do a new line over here. New line over here, and then I'll put the year. Okay. Cool. If you're curious what this print statement is doing, I was pretty brief about what the printf does. Printf is a function, a method that uses a little mini language. The little mini language is called a string formatter. So this %d is saying that there's going to be a decimal number here. Or no, not a decimal number, a decimal integer. So here, let me just pull it up. You can look up string formatters in Java. And then click on the primary doc. So the %d, what is that doing over here? I'm using this over here. It's a mini language. The d means we're going to be formatting it as an integer. So a year is an integer, and this year variable gets substituted into this %d. Okay, and then let me do one more statement. I'm gonna increment the amount, the year. So I'm gonna say, hey, year is now equal to a new value. That new value is just going to be increasing by 1. So I'm just gonna say set it to the previous year, but add 1 to it. Okay, so I do want to repeat that the right side is evaluated first, and then it gets stored to the left. That's kind of the directionality here. Okay, so let me go ahead and run it and see what it does. Okay, so I'm already in the directory, so let me Java compound interest .java. All right, people see what's happening here. So we have a loop. We see that the integer, it's getting bigger and bigger. It's never stopping. This makes sense because our loop right here is, there's a hard-coded true. So this is never going to be false. Sometimes it's necessary to use infinite loops. In this case, maybe it's not. So if you want to quit a program, so sometimes you might have an accidental infinite loop, which will make your program look frozen. So if that ever happens, then you can quit with Control-C, I believe. Control-C is a signal to the Java program. It says to pull the plug on it. All right, so I just press Control-C to quit the program. And just to show something real quick that it does pull the plug, I'm gonna put like a print statement at the end of it, like a print line. I'll just say end of program. Okay, so let me just run this again to show folks that pulling the plug means it doesn't really mean quit the loop. It means quit the whole program. So let me run the program again, Java, and what happens here? Oh, I got a compiler error. Oh, this is actually a pretty cool compiler error. Nice. So the compiler is telling me that I will never reach this. That's pretty cool. I didn't know it could know that. Okay. So you know what? So let me comment this out and put it later. Pretty much the compiler already knows that it's never going to get here. It sees an infinite loop here, so it's protecting us from something bad that might happen. Okay, so I'll revisit this in a bit. But anyways, when you have an infinite loop and you want to quit it, you can press Control-C. So there it is, Control-C. This is useful when, like, sometimes you don't know if you have an infinite loop. Like, let's say I were to comment out this print statement and run the program again. So I just ran the program, but I mean, it compiled it and is running, but there's nothing here, which makes sense because we commented all the print statement. The program is running, by the way. The year is getting bigger and bigger. We just don't have any print statements. So sometimes you can't see an infinite loop, and it's necessary to quit. So Control-C right here. Boom. Right. Control-C brings me back to the terminal environment. All right. Cool. So we are simulating the years. Let's go ahead and go to the next step. All right. We're going to do a quick class exercise just to make sure folks are okay with the while loops. So this is going to be a chance for you to play around with a while loop. Let's go ahead and take like 10 minutes for folks to play around with it. Let's go ahead and expand on this program and simulate a bank account getting bigger and bigger. All right, so far, all we did was simulate a year getting bigger and bigger. Right here, let me pull it up again. Yeah, we simulate a year getting bigger and bigger. Oh, you know what? I skipped over one thing. My bad, my bad. Here, let's back up a bit. I forgot to talk about how to make a loop condition false at some point. So currently we have an infinite while loop. Would folks know how to modify this program so we can stop when the year is 2030 or something? Right, like let's say we only wanted to simulate 4 years. How do we update the program so we only have 4 iterations? All right, hopefully people thought about that. We just have to change this condition. We have to change it so it becomes false at some point. So if we make the condition year is less than or equal to 20 or less than 2030, yeah, this is saying do the statement when this condition is true. So when the year reaches 2030, this condition will be false because 2030 is not less than 2030. So then this would quit the loop at the 4th iteration. So let me run this. Okay, cool. People see what's happening here. Okay, we updated the loop and now there's only 4 iterations. All right, in contrast, previously it was infinite. All right, so you could change this number here if you want. Like if I made it less than or equal to, then this means to include the 2030. So if I were to run this one, I have an additional iteration. All right. So yeah, now that we know how to make finite loops, we should be able to do this class exercise. Let's go ahead and update the program and simulate a bank account getting bigger and bigger. All right, there's a lot of flexibility here. You feel free to have fun with it. I will help folks with the setup. All right, so far all we have is a year variable, but let's go ahead and set up a bank account variable, like a savings or something. So here I'm gonna go ahead and make another variable. Let me represent like a savings account getting bigger and bigger. I'm gonna use a double because savings account. Because we're dealing with money. Money can have decimals, so I'm gonna use a double. I'll call it like savings, and I'll initialize it to 0. Let's say we have 0 money in our savings account, and maybe we have some sort of salary. So hypothetically, we're going to be gaining a yearly salary. I'm just going to code it in as a variable. I'll call it salary, and you can make up whatever number you want. I'm just going to say like 60,000. Say you make 60,000 in a year, and maybe we want to see this get bigger and bigger. All right, so with these 2 new variables, let's go ahead and let folks play around with our while loop. Let's do this class exercise. So let's give it like 10 minutes. The class exercise is to simulate the bank account getting bigger and bigger. All right. Yeah, let's give that like 10 minutes. All right, I'm gonna pause the recording. I'm gonna pause the recording right now. Let me just put a timer up here. Okay, let's put a timer. Okay. Pause the recording right now. All right, we are back from the 10 minutes. Hopefully folks gave that a shot. So here all we really had to do was add a couple lines in the while loop. I know some people might have made another separate while loop, like they might have done a while here, but it's actually not necessary. You can still reuse this one over here because it's going through a certain amount of years. But yeah, let's go ahead and reuse this while loop to make the salary bigger. I mean savings, my bad. So every year the savings is going to have a new value. So I'll say, hey, savings is now going to become savings plus the salary. All right, once again, the right side gets evaluated first. This is taking the old savings, adding the salary, and then storing it back to its original variable. So this is accumulating. All right, and let me go ahead and print out the savings. You know what? Let's see. Oh, you know what? Here, let me put this in the beginning of the while loop, actually. This way I don't have an off by one error. Because if I put it here, it's not going to show how much I started with. So let me move these up here so I can see how much we started with. Okay, so let me go here. Salary is, or no, not salary. Savings account. Savings is going to be some decimal here. I think. What do I put here? I'm trying to format a double into here. Let me look it up. What's the format for that? I think it's an L. No. Oh, it's an F. My bad. I forgot. Yeah, F stands for floating point. Floating point is a fancy word of saying decimal. So let me go ahead and format this percentage F. And let me do a new line over here so it looks neater. And then the savings right here. Cool. So savings will get, this variable is going to get substituted into this percentage F. All right, let me go ahead and test this real quick. Okay. Java compound interest.java. And okay, you know what? Here, let me clean this up a bit. This is a little hard to read. Let me clean it up. I'm just gonna make this rounded to 2 decimal places. So you can go period 2f, which period 2 means rounded 2 decimals. And then let me put another new line here so it looks a little neater. Or actually, I'll just print a bunch of equal signs. I'm just gonna print a bunch of equal signs. This way, every iteration, we can visualize it a little better. Okay, so let's go ahead and run that. And okay. Cool. All right, so we started off with 0. This is our very first print statement. And then the year is 2026. So then we're going to loop to the next one. The year becomes 2027, and then we check if the while loop is still true. Yeah, the condition is true. So we're gonna do this again. And then, yeah, this loops all the way until year becomes 2030. Year becomes 2030, we do our last iteration, and then a year becomes 2031 here. So then 2031 makes the condition false, and we will terminate from there. All right, people cool with this so far? Okay, cool. Let me see if I can change my workflow a bit. I don't really like how small my terminal is here. Can I just use a PowerShell? I'm just gonna use a PowerShell over here. Let's see. Okay, this should be a little neater. Okay, and then let me quit this over here. Okay, cool. This terminal is the same as what the VS Code had. So let me just CD into where I need to be. I need to CD into downloads, actually. CD into, yeah, downloads. And then I have a CS-12J, examples. And okay, cool. Java compound interest. Let me just make sure. Cool, there we go. This is a little easier to read. Okay, sweet. Any questions about this so far, folks? Okay, cool. Let's modify this program a bit to make sure folks fully understand this. How would we simulate? How would we figure out when we become a billionaire? Or like, how do we simulate until we reach like $1 billion or something? Yeah, this is hopefully people thought about it, and we have to change this condition. That we need to change this condition to stop when we exceed like $1 billion. So if we wanted to simulate that, we would have to change this to savings while the savings is underneath $1 billion. So let me put $1 billion here. Okay, that should be $1 billion. All right, so let's go ahead and run this. We should see it go. So there it is. It's running. And boom. All the way to the year 18,692. It looks like our savings was almost $1 billion. So on the next year, it exceeded it. So yeah, it looks like we become a billionaire in around this year, 93 to be exact. All right, people cool with this so far? Cool, cool. So yeah, all we're doing is simulating years and kind of visualizing variables. Hopefully people are okay with this so far. Okay. Let's see, how about $1 million? Let's see, let me just change it to $1 million. Let's run this over here. And okay, cool. That one ran a lot faster. So it looks like we become a millionaire by 2043. It is off by 1, but hopefully people can fix this around. Okay, here let's move on. So we did want to move to compound interest. That was the name of the file. So to keep things simple, let's go ahead and ignore the salary for now. All right, I'm gonna go ahead and comment out everything that has a salary. I mean savings that includes a salary. So let me get this over here. Okay, just to make things easier to understand. All right. So yeah, let's go ahead and simulate compound interest. So for folks who might have their own savings account, hopefully you're aware that the bank pays you to keep money in their vault. This is called interest. So you put in a certain amount of money to the savings, and then there is a rate, an interest rate that the bank will pay you off of. So let's go ahead and simulate that. Let's simulate like a savings account getting bigger and bigger again. So far we initialized it to 0 over here. Let me remove these salary things. Our savings is initialized to 0. If we were to put this in a savings account, we're not going to accumulate anything. Yeah, you know what I mean? So let's go ahead and initialize it to 2,000 instead. Like let's say I initialized my savings account 2,000, and we're planning on accumulating interest every single year. All right, so typically interest is accumulated a little differently. Not really every year. It's actually divided amongst months. But just to keep things simple, let's accumulate every year. All right. So how do we do this? For the sake of this scenario, let me create a interest rate. I'm just gonna set it equal to 5%. This is a pretty good rate, by the way. I think some banks are like 3%, 4%. I forget. Discover. I'm using Discover right now. They're at like 3.5%. So 5 is pretty good. Anyways, so if we have $2,000 and every year we gain 5%, how do we update this in the loop? Right, the loop needs to accumulate savings. Savings needs to get bigger. So let me say, hey, savings is now equal to what? Yeah, go ahead and think about it for a bit. Oh, here, let me change this condition actually. I'm going to change this condition back to years less than 2030. This way we only get 4 iterations, I mean. All right, so we're just going to simulate 4 years. But within each year, how do we accumulate savings? All right, well, it's equal to the old savings, but we have to add whatever we accumulated. So if we accumulate 5%, then that would be your whole savings multiplied by 5%. People see, oh, this is a magic number. I'm at interest. All right, people see what's happening here. So this thing in the parentheses is representing accumulated interest. If you wanted to make things a little more readable, you could save this as a variable. Like you could save this as a double and call it like accumulated interest. So every year we accumulate interest, which is equal to these two multiplied by each other. And then you could substitute it back into here. All right, so yeah, if you want to make things a little easier to read. So here, let me go ahead and run it again. So let's go ahead and run it. Okay, cool. So let's sanity check this to make sure. So in the very beginning, we have 2,000. Cool. Next year comes, now we have 2,100. Cool, that makes sense because 5% of 2,000 is $100. So let me just pull up a calculator. So 2,000 times 5% gives me 100. Right, so the accumulated interest is 100, and that's why we have 2,100 in the next iteration. But then the next year comes, and let's see. So let's see what happens. So next year comes, we accumulate a certain amount of interest. It's going to be equal to 2,100 because that's how much we have it there, multiplied by the interest. So let me go 200 times 0.05. 0.05. So in the next year, we have more. We accumulated 105. So that's why we have 2,205 here. And then for the next year, we have 2,205 times 0.05. This gives us 110.25. So that gets accumulated to the savings. All right, so yeah, people see what compound interest is. Where hopefully people notice that every year, accumulated interest became bigger. So that's why they call it compound. There's simple interest and there's compound interest. I believe for most of us, we care about compound interest. All right. So yeah, that's there. Let's modify it again. With a 5% interest rate, how would we figure out when we become a millionaire? You know what I mean? Like you put in money and you want to know when you reach a target. So how do we modify the program to simulate until we become a millionaire? Well, we did this earlier. All you have to do is modify this condition. Modify it so it keeps running while we're underneath the target. So that the target here is while the savings is underneath $1 million. All right, let's go ahead and run this. So let's see. When do we become a millionaire? Okay, it looks like by 2154 we become a millionaire. Cool. Pretty cool stuff, right, folks? People getting a sense on loops now. Okay. Let me check on the Zoom chat. Yeah, people are all good. Okay, great. For folks who are interested in math, you might have heard of this formula here, compound interest formula. So real quick, this loop is not a closed form solution. If you've taken an algebra class, you might have seen this compound interest formula. It's a continuous one. Hold up, it's not this one, is it? It's a continuous one. Let me look it up. Continuous, yeah. For folks who might have seen this formula here, this is saying your final amount is equal to your initial, times e to the rt. E is a constant. If you're ever curious how this formula was made, if you've taken like a calculus class before, like Calc 5a, this formula is made from taking the limit. Oh, they have a picture here. Nice. If you take the limit of this loop right here, then you end up with a certain formula. So you could look this stuff up. It's not really part of the class, but you take the limit as the loop goes to infinity, and you end up with this A equals PERT formula. It's pretty cool stuff. So yeah, this is a closed form. This is a closed form solution that is derived from running this loop an infinite amount of times. All right, let's move on then. So let me save. And where are we at? Okay. All right. So we did one example, compound interest. Let's go ahead and move on to a guessing game, a glorified guessing game. Let's talk about roulette. This is like a gambling game where you bet on a number, and if the ball lands on that number, you pretty much win. So I'm gonna look up a random one real quick. I'm gonna look up a random roulette simulator to see if roulette simulator. Let's play roulette for a quick second. So let's see, this one a good one? Yeah, probably. Let's see, play for free. Cool, so this is a simulation. We see that there are a bunch of numbers here. We have a bankroll. What's our bankroll at? Our bankroll is at 1,000. So the game works like this. First, we pick up a chip. So let's say I pick up $5, or here, let me pick up $25. So let's say I pick up $25. The next step is to choose where to bet on. So there's a bunch of numbers. There's also like odd and even, and there's red and black. Let's keep it simple for now. Let me bet on black. So there you go. I put 25 chips on black. Let's go ahead and spin the wheel. So now the dealer is going to spin the wheel, and the thing is going around.
8 black even. You
okay.
Win.
Cool. So it landed on 8. This is a black number, so we won. But how much did we win? So we won 1-1. People know what I mean. You see how we have 1,025 now, but we started off with 1,000. So if we end up in one of these, this is like a 50-50 scenario. It's not really 50-50, by the way, because of this zero here. But we get paid 1-1 on these over here. Same with the even or odds, because this is like almost 50-50. All right, but let's say I were to bet money on like an individual number. Like let's say I bet 25 on 15. All right, so let me put $25 on 15, and let's say we're done betting. So now the dealer is going to spin the wheel. All right, so dealer spins the wheel, and hey, here, think about it. If I land 15, how much money should I get?
24.
Okay, well I didn't land on 15. It landed on 24, so I lost my 25 chip bet, and now I'm back to my original bankroll, 1,000. Right, let me keep betting on 15. Maybe someday I'll win it. But yeah, how much should it pay? Right, if I land on 15, is it gonna pay 1-1? No, that would be super unfair. Okay, so there you go. I lost 25 chips right there. But yeah, let me just bet one more time. If I land on 15, there's a payout. Different casinos are different. I believe this one should pay like 35-1.
18 red even.
Okay, I lost that one too. So if it did land on it, it should pay 35-1. So let's go ahead and simulate this. For the sake of this demo, let's make it simple. Let's only care about this certain bet. It's called a straight. A straight is where you bet on a single number, and if we land there, then it pays 35 to 1. All right, just to keep things simple. Later on, you can upgrade it for like even and odd. You can upgrade it for red and black, and all of those other things. All right, but straights pay a lot, 35 to 1. So let's go ahead and simulate this. Right, so I'm gonna go ahead and make a brand new file. Let me make this file. Whoops. I'm gonna call it. Whoops, this is in the wrong folder. Let me put it in the examples folder, and I'll call this roulette.java. Right, there we go, roulette.java. Okay. All right. First thing is first, we should probably think about the variables we'll need. All right, what variables do we need when we are playing this game? Well, one is the bankroll. So I'm going to represent as an integer just to keep things simple. So I'm going to declare a bankroll. Bankroll. This is like how much money you bring. Like say you enter the casino and you usually maybe bring some money. Okay, so bankroll. Let's say I brought in like 200 bucks. So I'm just gonna bring in 200. Okay, cool. So we have a bankroll. Let's simulate a round. All right, but I'm gonna do it in a loop because we want to do it over and over again. So let me set up a loop here. This is a while loop. This loop is going to be pretty much saying while something, play a single round of the game. All right, earlier we played like 4 or 5 rounds, and here we're going to play a certain amount. All right, so for this condition is going to represent when we play the game. All right, so what condition should be here? Well, there's actually a lot of conditions you can do. There's a lot. But to keep things simple, when do people stop gambling? They typically stop when they run out of money. So one way you could represent this loop is by saying while they have money, force them to play. You know what I mean? Just to keep things simple. So while they have money, this is what the condition is saying, then play the game. All right. So let's go ahead and play the game. Let me pull up the roulette simulator again. So what should we do in this while loop? What's the first thing we should do? Well, there's many things, but one of the first thing we probably should do is handle input. Like back to this game, you see that the first thing we did was kind of choose a chip. Like here, first thing I did was I said, okay, I'm gonna choose the 25 chip. So this is like input. I'm telling the program how much I'm planning on betting. So let's go ahead and take input for that. So I'll ask the user, how much are you wagering? So I'll say, how much are you wagering? And then let me put a $sign here. You know, I don't need a printf here actually. Yeah, I don't need a printf because I'm not planning on putting any variables in here. So how much are you wagering? And let me go ahead and take input. Let's see, I'm gonna use a scanner actually to take input. So I'm gonna declare a scanner. I'll call it input. You can actually call it whatever you want. Okay, I'm gonna use a scanner. This is more powerful. I'm gonna create a scanner from the system in. System in is a fancy word of saying standard input. And for us, standard input is on the terminal for now. But later on, we're gonna be taking input from files and stuff. So yeah. In short, system.in is like saying our keyboard. But later on, it could be files. We can scan files and go through them. Okay, so I'm gonna use a scanner here because it's very powerful. It makes things a little easier to read too. Like this input object has a function called next int. Next int, it pretty much allows the user to type something in, and it'll store it as an integer. So since it's returning an integer, here, let me pull this up real quick. So scanner Java, just in case folks aren't sure what this is. So scanner in Java, I'm going to be using this method here. Next int. I'm using this method over here. It's a scanner method that scans the next token of input. Next token is like something we type in, and then it returns an integer. So it might be useful to store this. I am going to store this in a variable because we're planning on using it later. So I'm going to store it as integer. I'll call it wager. All right, so there's integer wager, and then let me take another input because we need to implement like what number you want to bet on. You know what I mean? Like here I chose a number, so I'm going to wager 25, but now there's another input. Where are we going to put that number? Like so let's go ahead and ask them. So I'll ask the user, what number are you betting on? Okay, what number are you betting on? And now let me go ahead and take input .next int. Let me store this as like an integer again. Once again, this is just like our guessing game. Okay, I did type quite a bit. It's probably a good idea to sanity check just to make sure things are compiling and running. So let me add in one more print statement. This is a sanity check. You don't have to do this. I'm going to sanity check these two inputs to make sure the program took them in correctly. Okay, so let me go system.out.print, and let me use a printf here because I want to put these two variables inside of a string. So let me just echo it back out. You're wagering some some number on the number, some number here. Okay, so there it is. I have two formatters here, by the way. I'm wagering some amount. Oh, let me put a $sign here. So yeah, let me put a $sign. This way, this number looks like money. So you're wagering something on the number something. Since we have two string formatters, we need two additional arguments to this function, which is going to be the wager and then the guess. How this works is the wager gets substituted into this %d, and then this guess also gets substituted here, this %d. Oh, let me do a new line. And let me print out one more thing. I'm just going to print out a bunch of equal signs so it looks neater on each iteration. Okay, there it is, bunch of equal signs. And okay, it's probably a good idea to test now. So let me get ready to test this. Okay. Let's see. Okay, let me type in Java Roullete. Java, enter. And okay, cool. So we entered in the while loop. We entered the while loop because the condition is true in the beginning. 200 is greater than 0. So now the program is waiting for an integer. I'll go ahead and type in like 25. 25. Enter, and now the program says, what number are you betting on? Let's say I bet on the number 15, lucky number 15. And then let me go enter. So, okay, cool. I pressed enter, and then, yeah, here's a sanity check that I was making sure right here. So the sanity check is you are wagering 25 on the number 15. Okay, cool. So it looks like we successfully took in the two inputs. And so you see what's happening here? We're in the next iteration of the loop. After these equal sign, it's now waiting for another input. These two over here. So let me test it again. Like let's say I bet $50 now. I'll go 50, and then what number are you betting on? Let's say I put on 15 again. Enter, and you are wagering 50 on the number 15. Okay, cool. So we successfully sanity checked the inputs. Let's go ahead and move on. All right, what should we do next? Well, once we have these, here, let me remove this sanity check. Once the user puts in their bet, what should happen next? The ball should roll. You know what I mean? Like, once you're done betting, the dealer is going to roll the ball. Roll the wheel or ball, whatever. Okay, so let's go ahead and roll the wheel. Since we're in a program, we could just generate a random number. Okay, so let's go ahead and generate a random number. You might remember this from last week. Last week we wrote a guessing game, and we used this random class from this over here. Let me pull it up. So there's a random class. This allows us to make objects that will make it easier for us to generate random numbers. So we're going to be using this method over here. So just a quick refresher on how this works. Let me pull up a J shell over here. Oh, you know, let me quit this program right here. So I'm quitting this program because I want to go into the J shell. So Control C quits. Let me clear. Okay, let me enter the J shell. Enter, and okay, I'm just gonna show what this is doing from last week. So this first line, I'm creating a object from the class random. I'm gonna name it RNG for now. You can actually name it anything you want, but I'm naming it RNG for random number generator. Right, and then the right side is saying make a new one. This will make sense probably towards the end of the semester when we talk about creating objects. Okay, so how this works is this method or this object has access to a lot of methods, like next int. This is kind of like our scanner one. You remember in our scanner one, so this is the input.nextInt. This is a little, it's kind of the same. The similarity is that the method returns an integer. So for the scanner, it grabs input from the keyboard, and then it returns an integer. This next int over here. But with this RNG object, the next int is very similar. It generates a number and then returns it. So in this case, it gave me this number, and I can run it again. It's giving me another number. Run it again. See how now it's giving me negative numbers. So yeah, this method in this very first is giving us a range between the smallest possible integer and the biggest possible integer. If you're curious what these values are, you could revisit like the second lecture, the second or third lecture, I forget. But we talked about integer overflow, and but basically the primitive integers, they have a certain range to them. The min value, it's like negative 2 billion something. Let me check. So let me go integer dot min value. Let me just see what this evaluates to. So yeah, it's negative 2 billion something. And then the max value is positive 2 billion something. So if you're curious how these numbers are, they're not random numbers. This is actually is representing how many numbers we can store in 32 bits. So with 32 bits, this number comes from it comes from 2 to the 31st power. So 2 to the 31st power. See, I need a scientific calculator. So 2 to the 31st power You see this number here, it's 2 billion something. That's kind of where these numbers are coming from. It's showing with 32 bits, we have a certain range. All right, so anyways, our rng.nextInt returns a number, but we should probably constrain the range. In Roulette, there are a certain amount of numbers. Here we have 0 all the way to 30 something. It's like 36, I believe. I think there's 37 numbers, 0 all the way to 36, I think. Let me check. Yeah, there is. So we need to find a way to generate a number between 0 and 36. So you could look at this documentation. That's where I pulled this from. You could look up random. So this is the random class, and then there's a method called nextInt. So here's a nextInt right here. It returns the next random number. So in particular, there's one here that takes an extra argument. An argument is data that you give to the method. In this case, the argument is called an integer bound. This argument will affect how the method behaves. So if I were to put like 6 over here, so let's say I put 6 as an argument. So I'm telling the method to work with this number. So I'll run it and we get 4. Run it again. Whoops, I made a typo. Run it again and get 4. Again, 5, 1, 5, 3, 0. Cool. So by putting this upper bound here, it's saying that our range goes from 0 to 5. Because 6 is exclusive. The bound right here, the specified value is exclusive, meaning it is not included in the range. All right, so there's many things you can do. You can also add one here. This is like a dice roll. You know how dices have 6 sides? If you wanted to simulate a dice roll, you would add 1 to it. Because by adding 1, it's shifting. It's offsetting this whole range by 1. So yeah. Once again, if you wanted to simulate a dice roll, you just add 1 to this. So 2 and 6. Yeah, these are all dice numbers now. All right. So with the roulette simulator, we should probably generate a random number between 0 and 36. So before I roll the wheel, we have to declare the object. So at the very beginning of main, I'm going to go ahead and declare it. Well, we only need to declare it once. So I'm going to declare it. I'm going to say, hey, let's go ahead and make a random. I'll call it RNG. You can call it whatever you want. And then this is going to come from the random class. Whoops. Random. Okay, cool. So there's a new line. This is object-oriented programming, by the way. Here, let me put a. This is a sneak peek into OOP, object-oriented programming. So I know this might be a little hard to understand, but it'll make sense when we talk about objects. Okay, so we made an object called RNG. We can go ahead and generate a random number. So I'll go nextInt. And since we're planning on generating from 0 to 36, we have to put 37 in here because 37 is exclusive. Right? This is this generates a random number between 0 and 36. Right? This also returns an integer, so I'm gonna store it into a variable because I'm planning on reusing it. I'm planning on using it in a decision tree. Yeah, you know what I mean? Like we do have to make a decision tree to figure out whether or not they won or lost. So I'm gonna store this into an integer. I'll call it like roll. Okay, so roll, and let me do a print statement here. You don't have to. Oops, let me do after actually. So after here, let me go. Ball landed on some number. Just so I can sanity check this roll over here. So ball landed on some number. So I'm gonna put a D here. D stands for decimal integer. and then let me put a new line, and then the digit, the decimal integer is going to be roll. Okay, let me go ahead and test this real quick to make sure it's working. Okay, I need to quit this J shell though. So yeah, let me quit this J shell. Okay, and then let me run it. Compile, Okay, cool. Compiled it. How much are you wagering? Let me put in like 25 bucks. What number are you betting on? Let's say I bet on the number 15. And oh, I was pretty close. So it says ball landed on 14. So this means I lost 25 bucks. And then now it's looping to the next part. Oh, do you want to wager again? Or how much are you wagering again? Cool, so let me just test the input again. Let's go 25 and bet on 14 this time. So 14, and this time the ball landed on 27, so I lost again. But yeah, this is an infinite loop, by the way. People see why this loop is infinite. It's infinite because bankroll is always positive. We never implemented logic to decrease the bankroll. So yeah, we're in an infinite while loop. So it's probably necessary to quit. So I'll press Control C to quit, so we can carry on with the program. Okay, so let's go ahead and make a decision here, because when we're finished rolling the ball, we should probably make a decision whether or not they won or lost. So did they win or lose? Well, this is a decision tree with 2 branches, so you could represent it as an if statement with an else. Right, the else where the first is false. So let's say we won. Well, winning requires our guess to be the same as the roll. So guess is equal to roll. This is when we win. So I'm gonna say, let me put, what happens if we win? Right, what happens? If the ball lands on a number, then the bet pays 35 to 1. So this means our bankroll will get bigger. Our bankroll will get bigger by the original bankroll, right? And added whatever the award is. The award is our wager times 35. Let's see, 35 is actually a magic number. Let me go ahead and give this a named variable. Let me go on top over here actually. So this is kind of like rigging the machine. You can declare payouts at the top. So I'll declare a payout here. I'll call it. I'll make it constant. Final integer. I'll call it straight payout, and set it equal to 35. This is a better programming practice because it's saying that the straight payout is not a variable. It's a constant. A final means that straight payout is not allowed to change. So you're kind of preventing future people from modifying the straight payout. It's like a security thing. You're making something impossible to change. So here I'm going to put straight payout. This is the named variable. Okay, so you see what this is saying? Once again, the right side gets evaluated first. I know I keep repeating that, but it's a very big takeaway from a lot of programming languages. The right side gets calculated and we store it back into the original variable. Right, so what happens if we lose? If we lose, do we lose the wager times the straight payout? No, we don't. That would be super unfair too. We just lose our original wager. So this is going to say bankroll is equal to our original bankroll, but subtracted away what we lost. Right? Cool, so here's the decision tree. It's probably useful to tell the user how much money they have left. So let me tell the user how much money they have. Your bankroll is now, and then I'm gonna say it's a decimal number, decimal integer, and put the bankroll here. All right. Oh, let me put a $sign in here. $sign. This way it looks like money. Okay, cool. Let's go ahead and run this. So compile. Okay, cool. It compiles and it runs. So how much are you wagering? Let me put in well, I started off with 200 bucks. So let me put in like 25 bucks. This is an eighth of my bankroll. So, okay, cool. Bet 25 bucks. What number are you betting on? Let's see. I bet on number 15. This is my birthday, February. And let's see. So it went pretty fast. The ball landed on 20. We lost. So yeah, our bankroll is now 175. Let me bet 25 again on the number 15. I'm gonna keep playing 15 until I win or lose. So enter, and ball landed on 0. Okay, that's unfortunate. So now my bankroll decreased. Okay, let's run it again. So 25, enter, 15. Okay, I lost again. Back down to here. Let me keep betting. 25, 15. Okay, lost. 25, 15, lost. 15, lost that one. 25. Okay. Okay, I lost again. I'm down to my last $25. So let's say I'm wagering $25 here. And then what number are you betting on? Let's say like a 15 again. Okay, here's my final one. So enter. And ball landed on 17. Bankroll is now 0. So the bankroll became 0 over here, which makes our condition here false. 0 is no longer greater than 0. So we terminate the loop, and that's the end of the program right here. Let me put a thank you here. Print line. I'll say something like thank you, come again. Okay, let me just play this one more time. So let me see. Okay, so we start off at 200. Let me run it again. How much are you wagering? 25, 15, 25, 15, 25, 15. I'm running it really fast. 25, 15. Okay, here it is. I'm down to my last $25 again. So I'll go 25 and 15. And I lost that one. Thank you, come again. So yeah, I never won. Here, let me play it one more time. I do have like a 1 in 37 chance of hitting it. So maybe by now it's due. So let me run it again. 25, 15, 25, 15. 25, 15. Oh, there it goes. I ran out of money again. So in a real life scenario, I would have lost like 600 bucks right there, because this is my third time playing. Let's say I play again. So now I'm 800 bucks deep. So 25, 15. Okay. 25, 15. Okay. So now I never won. I'm 800 bucks deep now. But if you're playing this, there's a chance that you might have gotten a different result. Okay, so people seeing what's happening here though, we have a loop that this loop pretty much says play while there's money, or force the user to play. Force the user to play while they have money. That's what it's saying. In practice, you probably want to validate certain numbers. This program is super flawed, by the way. Yeah, you know how flawed this program is? It's here. Let me run this program again. What do you think is going to happen if I wager a negative amount? Like let's say I wagered negative 500. All right. So here we start the program over again. So our bankroll is at 200. Okay, if I bet negative 500, what do you think is going to happen? Okay, let's see. Is it going to break the program? Enter. No, it didn't break. Okay, what number are you betting on? Let me bet on the number 15. It doesn't matter as long as it's between the 0 and 36. But let me press enter here. And what do people think what might happen? Well, I actually don't know because there's random number generator. But what do you think would happen if I didn't land on 15? All right, let's see. So ball landed on 5, which means I lost, but now my bankroll is increased to 700. Right, people see what's happening here. So let me try that again. Let me say I'm betting like negative 300 now. So let's say I bet negative 300 and then enter. What number are you betting on? Let me bet on 15 again. And what do you think is going to happen if I don't land on 15? All right, well, if I don't land on 15, it's going to do this over here, bankroll minus wager. And this is going to, yeah, so that's what happened. So ball landed on 3, which means I lost. And the losing branch is right here. Hopefully people see what's happening though. We subtracted a negative number. So by subtracting a negative number, it makes us add. Right? So people see the flaw in this program. As we heard last week, there are a lot of room for error, especially during input. Programs are really fragile during input. If people are aware of your code, then they can probably take advantage of the input. So yeah, if people like let's say you deploy this as a real game. If people are aware of the logic behind the game, then they can pretty much hack the input by putting in negative numbers and getting more and more money. So in practice, you want to protect everything, like every input actually. So if you want, this is a really good use of lab time. Let me put a fix me here, or to do. This is like a good class exercise. The class exercise is maybe to protect all inputs from in particular probably like bounds checking. Bounds checking means to make sure the number is within a certain range. Like with this wager right here, that this is an input. It would probably be appropriate to check to see if the wager is within a certain range. You know what I mean? Like first of all, it's got to be positive, and second of all, it shouldn't be above your bankroll. You know what I mean? Like if I run the program again, it is possible for me to bet like 1 million. It's totally possible because there's no protection here. So I'm betting 1 million. We bet on 15. And and now I'm like super negative. So yeah, by bounds checking, you probably to do bounds check. Let me put a to do here. So to do bounds check, and then maybe here you want to do a bounds check as well. In the second input, like what number are you betting on? Well, we need to protect people from betting on out of bounds numbers. Like let's say I bet $25 on the number 50. So first of all, the number 50 doesn't exist on the roulette wheel, but the program is still going to let us do it and lose anyways. So it also might be necessary to bounds check this guess. All right, so you should try this. It's a really good use of lab time. The best way is to make some sort of decision, like if it was outside of a range, then maybe ask again. You should think about it. If you're curious, it's probably gonna look like a while here. Like it's probably gonna look like an inner while loop. So you could think of it like this over here. You could think of it as while their input is invalid, do it again. You know what I mean? So how do we represent if the wager is invalid? Well, the wager is only invalid if it's less than 0. If it's less than or equal to 0, this is out of bounds. Or if the wager exceeds your bankroll. Your bankroll right here. So this is saying if the wager is negative or if the wager exceeds our bankroll, then ask the user again. So let me ask the user again. System.out.print. I'll say invalid value. Try again. And then put a $ here. So put $, and then let me take input again. I'm gonna reuse this local variable, by the way. So there's no need to redeclare like an int wager. There's no need. And actually, if you do redeclare an int wager, this variable only exists in the while scope. So it's not going to be using the outer one. Meaning that down here, in this decision here, the wager would be dealing with the outer one over here. So yeah. Anyways, just go ahead and reuse the wager here and then set it equal to the another input dot next int. All right, so this is called bounds checking. So this is called bounds checking. It's like a safety thing. All right, let me go ahead and save this. So save and test. I need to quit this program. So Control C. Let me clear this. And then let me run it. Java. Okay, I'm gonna go ahead and test. Oh, I'm missing a semicolon. My bad. Let me look. My goal is to test this bounds check over here. So how much are you wagering? Let's go. Let's say I bet like $201. So I'm betting 201. It says invalid value. Try again. Right. You see why it's invalid? It's invalid because our wager exceeded the bankroll. So once again, this is an OR. This is a Boolean operation, meaning that any of the sides gotta be true. All right. If any of the sides are true, then that means the whole thing is true. That's what the OR means. So let me try again. Let's go like -50. -50 right here. Enter. Boom. Okay. Invalid value. Try again. All right. This is true because now the left side is true. All right. But finally, let me type in like $20. So let me say 20, and then enter. Okay. Cool. So 20 is a good number. When I typed in 20, both sides are false, meaning that the while loop is no longer done. So since both sides are false, we're now going to go to the next input. What number are you betting on? All right. So yeah, people getting a sense on what it means to make a robust program. Programs are really fragile during input, so it's a good idea to protect it. All right. So yeah, here let's summarize real quick. I know this is a little hard to read because there's like a loop inside of a loop, but in short, this outer loop is saying play around. All right, and then this inner loop is saying enforce a valid value. All right. Okay, and I do want to encourage folks to have proper indents. Typically, whenever you see a curly brace, things should be indented. Like you see how in the main there's a curly brace here. A curly brace means that there's a local scope. So by indenting, it tells the reader how deeply nested in it is. And then here, while there's another local scope. So that's why I indented everything an extra layer here. It helps the reader visualize the structure of your program, that they're able to see what statements are inside of what scope. My programs will get bigger in the future, so this is going to be really good program practice. All right, check it out. If I were to not indent anything, you know how hard this would be to read? Like here, let me unindent everything. Okay, if it weren't for indents, you see this block right here? This block, upon first glance, it looks like two separate while loops. It looks like one while loop that's working independently of another one. That's what it looks like. But it's the indents are kind of messing it up. You know what I mean? This while loop is actually inside of this. So by indenting, we can easily, well, not easily, but an average programmer can easily read the control flow. All right, so yeah, that's why indents are important. Okay, any questions about this? Pretty cool stuff, right? Yeah, feel free to spend some more time on this. It would be a good use of lab time to play around. Like maybe I would probably add in some color. This is a pretty hard game to read right now because it's black and white. You know, if you wanted to make things more colorful, like maybe the color green, or maybe make it red if you lose, make it green if you win. Yeah, you can go ahead and do that. All right, but the whole point of this demo was to show the logic. We'll do graphics later, by the way. We'll do graphics. I hope people aren't getting too bored with this black and white terminal. The first half of this class is gonna feel like grammar school, but it's really to make sure we understand the logic before we move on to actual graphics. Because if we don't know the logical flow, then it's gonna be a lot harder to implement graphics. So hopefully people are okay with this for now, just getting the syntax and the logical flow down. All right. Any questions on this? Okay, great. So we're gonna end like 5 minutes early today, but let me give some concluding thoughts real quick. So today we went in depth on the while loop. On Wednesday we're going to do more on the while loop, and also introduce a for loop, and then we'll introduce another assignment. This next assignment, the third one, it's pretty much going to be use a loop to do something. I haven't published it yet, but it'll be out probably tomorrow. All right, and then next week we'll do some common algorithms. This is the tricky part of class. Kind of thinking about how to solve a problem, but some problems require repetition. Okay, so next week we'll do some stuff on FizzBuzz. The FizzBuzz is like an interview problem. It's an analogy. If you're planning on working at like a tech company, it's highly likely they're gonna ask you, can you write a loop? It's highly likely, and then they're gonna ask you it as a technical interview, meaning you're gonna have to do it on the spot. So yeah, we'll do some common loop algorithms next week, but for this week we're just gonna introduce the while loop and then the for loop. All right. These are pretty much the same, by the way. They are the same structure. It's just that the for loop is like arguably cleaner. Okay, let's end it here. Thank you all for being here. Have a good day. Bye bye.